Over the next few years, global demand for AI compute power is expected to increase 1,000-fold as models are integrated into complex, real-time workflows. This chart compares that trajectory against projected hardware improvements. Even with significant gains in chip efficiency, physical manufacturing limits mean hardware alone can likely only provide a 10-fold boost, leaving a massive deficit in capability. This gap highlights the problem of inference, the sheer amount of processing power required to generate answers once a model is deployed. The constraint is largely built into the software. Most modern language models use an autoregressive architecture, which is inherently limited by how it processes information. However, a different structural approach is beginning to emerge, one that moves away from building text in a strictly linear sequence. This shift is rooted in 2019 research from Stanford professor Stefano Erman, who began developing an alternative to the standard sequential model. That research has now been applied to a commercial scale with Inception Labs' Mercury 3. Mercury 3 is a diffusion large language model. Rather than predicting one word after another, it starts with a rough initial guess and iteratively polishes the entire answer until it is correct. If software efficiency is the only way to bridge the compute gap, the industry may find the solution in moving away from sequential generation toward this model of parallel refinement. To see why that matters, we look at how traditional models work. They calculate one token at a time, appending each new piece to a growing string. Because this process is linear, each step must wait on the one before it. This creates a structural bottleneck. Modern data centers are built for massive parallel processing, but autoregressive models force these chips into single, serial tasks. Another issue is finality. Once generated, a word is permanently locked into context. If the model makes an early error, that mistake becomes the foundation for every word that follows. Steering around this error is what leads to the hallucinations common in today's AI. These systems are physically limited by their own logic, forcing a choice between slow generation or reduced quality. Diffusion takes a different path, borrowing a technique from image generators. They start with random static and slowly rearrange the pixels into a clear image. The challenge for Stefano Erman was applying that logic, originally meant for smooth, continuous data like pixels, to rigid, discrete building blocks of text and code. In a diffusion LLM, the process starts with a full grid of random words or noise. It functions like Wordle. You don't guess one letter at a time. You guess a whole sequence, then see which parts are correct and which need replacing. During the first pass, the neural network evaluates the entire response globally, looking at the full sequence at once. It identifies which tokens are correct and which are errors across the entire answer simultaneously. Through successive passes, the model discards the noise, refining the answer until it is fully resolved. To make this viable, Inception Labs uses reinforcement learning to train the model to converge faster, reducing the number of steps needed to reach the final output. Because the model is trained to fix mistakes rather than just predict the next likely word, it extracts more semantic understanding from its training data. This iterative approach allows the model to identify and correct hallucinations in real time, resulting in higher potential accuracy before the text ever reaches the user. This software logic is designed to synchronize specifically with the hardware found in modern data centers. Most high-performance GPUs rely on SIMD architecture, single instruction, multiple data. SIMD is built to perform the same task across thousands of data points at once. It is the definition of parallel processing. Sequential models essentially waste this potential by forcing these chips to work on one token at a time. Diffusion models map directly onto this parallel architecture. This diagram shows how the entire token grid is processed by the GPU simultaneously. Every time the Mercury 3 neural network runs an evaluation, it modifies many tokens at once across the entire sequence. This parallel execution is what allows the model to achieve a 10-fold increase in throughput compared to traditional architectures. It can handle a much higher volume of output for the same amount of computational effort and cost. By aligning software logic with the native design of the GPU, Mercury 3 bypasses the structural bottlenecks that have limited the scale of AI deployment. In terms of throughput and latency, Mercury 3 achieves Pareto dominance over speed-optimized models like Claude 3 Haiku and Gemini Flash. For any given speed, it is 5 to 10 times cheaper. Alternatively, at the same cost, it generates responses 10 times faster. These efficiency gains are achieved while maintaining the high-quality instruction following required for enterprise-grade applications. For developers managing high-volume workloads, the efficiency of diffusion makes older sequential models look increasingly obsolete. This speed is critical for latency-sensitive tools, like voice agents, which require sub-second responses to avoid the awkward pauses that break natural conversation. It also powers high-throughput customer service bots that need to manage tens of thousands of simultaneous queries without high costs. For developers, it provides code suggestions that stream as fast as they can type, removing the lag that can interrupt a workflow. Integrating Mercury 3 into an existing stack is straightforward. Because it uses an OpenAI-compatible API, switching models is as simple as swapping an API key. For organizations with high privacy requirements, it can be deployed via AWS Bedrock with provisioned throughput for dedicated performance. As the demand for AI grows, the industry is moving away from simply predicting the next word toward a future of refining the best overall answer.